Hello everyone, we are ready to do lab 5, which is real-time physics lab integrated into the IOLab system. And I've already opened the IOLab screen. Okay, so software installed in my computer. So let's go to the IOLab. We are doing lab 5 today, and these real-time physics labs have been developed in the collaboration of these universities. Okay, so let's do lab 5. Okay, the regular thing, you can see the dongle is not there, lab is not turned on. So what you can do is here the video. So regular, I'll just insert the dongle into my computer. Okay, then you'll see these things turning on. Okay, okay. See, this is paired now. Let me turn the lab device as well. Yeah, turning will turn. So you can see this has also turned on. Now they have been connected. Yeah. So you may go ahead. Do not forget to write your name in the first slide. Yeah. So go ahead, write your name. And in the last lab, we saw the relationship between force and acceleration when they were moving in the same direction. Now we'll be seeing in this lab how they will behave when force when they are in different direction. Okay, so force and the direction of the acceleration of the object. Yeah, we did that one. Okay, so let's you may go ahead, write your name, and then click on save and go next. Okay, so this will all be about force and acceleration relationship again. Okay, and then we'll be doing different kinds of motion. We'll be changing the mass. Okay, let's write your name, click, don't forget to click on save and go next. Okay, in the last lab we did the experiment when velocity, force and acceleration were in the same direction. Yeah, all of them had the same sign, not the direction but the same, they had the same sign. And in this we'll need these things to do the lab in this one. Okay, you can click on save and go next. After that we'll be slowing down, basically like we'll use the same technique that we used previously. So again, positive y-axis is the y-axis where your force is from double wheel towards the single wheel in your IOLab. Okay, I have seen people doing mistake considering that. Okay, so let me remind again, this is the one shown in your device. Okay, from single wheel to double wheel. But while doing the experiment, positive y-axis is from double wheel towards the single wheel. Okay, so positive y-axis will be like this for the motion. Okay, so we'll set up our device like this one. Okay, this force sensor is this side, positive y-axis is this side, and after you can click save and go next. Okay, okay, in this one we'll see how the acceleration and the force behave in this situation. Yeah, slowing down like we did previously when we apply, and like if we give a push from this side to that side, this mass will always pull that IOLab. Yeah, and it will slow its speed. So this is our positive direction, force is being applied in positive y-axis. Yeah, okay, you can click on save and go next. Okay, so okay, suppose that you give a IOLab push toward the left, and the diagram shows the position and the IOLab times. Assume that the IOLab is moving toward the left at all 4 times. Okay, what are the signs of velocity, force and acceleration when the IOLab is at y1? So since we already know velocity will have the same direction, same sign as the direction it is moving in. So if it is moving in negative direction, it will have negative sign. If it is moving in positive direction, it will have positive sign. Okay, so what are the signs of the velocity? So you may go ahead, make a decision. I already give the kind of answer. Okay, this is instructional video. I'll give the concept but not the answer, so you have to write your own answer. Velocity will have the same sign as the direction it is moving in. So it's moving in left, it's moving negative. Okay, okay, for the force, so we are applying the force in positive y direction, so you may go ahead and write what's the sign of the force. Okay, and for the acceleration, you can say it in two ways. Okay, so the regular concept that we have is, if we are moving in a direction and slowing down, the sign of the acceleration will be opposite to that direction. If we are moving in a direction, speeding up, sign of the acceleration will be same as the direction. Okay, and now right now we are slowing down, so it has to be opposite That's one concept, or this is directly related to force also. Yeah, the other concept. Okay. You may go ahead. So you may go ahead and predict at y and y2 using the same concept. Okay. Compare the magnitude of the velocity at y42 and y42 the velocity at y1. Is the magnitude greater here or here? We are slowing down, remember. Okay, so go ahead, write your answer and click on save and go next. Okay, in the next slide we are asked to compare the magnitude of the force at y4 to the force at y1. Okay, so we are applying same force. Yeah, we have not changed the force right now, so the constant force is being applied to this IOLab, so which is in the we are applying force in this direction, yeah, with the hanging mass. So force, there is no other force being applied, so it should not change. So go ahead and make your write the answer for that one. Okay, how will they compare? Will they be same or different? Compare the magnitude of the acceleration at y4 to the acceleration at y1. So you can write it based on your force, whether it's constant or not, or so acceleration is the rate of change of velocity, yeah, and we are slowing down with a steady rate. So you may go ahead, write whether it will be same or other thing. Okay, so for the force, it should not change. There is no any external force being applied here. So what we are pulling is we are just giving a force to this side with the hanging mass, and that doesn't change so during the muscle. So go ahead, write your answers. Okay, and we'll see when we do the actual experiment. Okay, what happens? Click on, after writing the answer, do not forget to click on save and go next. Okay, now let's do the real experiment. Yeah, so we are asked to do re-zero sensor. Okay, facing, I have used a string. I have the IOLab. Okay, and that's a general string I have used. Whether you can see or not is here. Okay, so they want us to re-zero the sensor. So you can click on re-zero. While re-zeroing makes sure that nothing is like being pulled and nothing is weighted here. Okay, and if you have graph already in there, that should not be selected while re-zeroing. Okay, so just click on re-zero sensor. Okay, and then let's make up the circuit that we here asked for. No, that's not the one. Okay, that is the one. Okay, let's make like this. We'll have 40 gram thing I have created with the water bottle, 40 gram. Okay, you may buy the real weight also. So I'll just hanging with the paper plate. Okay, and then okay, let's go to the real flows which we are supposed to do. So we're on slide 6 here. So we're doing this one. So we have bridge error, click record, give the IOLab a quick, very short push toward the left, and when the IOLab has come to the stop with your hand, prevent it from returning to the right. So we have to stop it. We will give a push from here, yeah, and then we will stop it when it is like this thing. I have just kept it to make sure it was that called. It is smooth. Okay, it's better to have a round thing so that the friction created by this can be ignored. This edgy thing. So let me put it like this here. And just pull it. Okay, so it is being constantly pulled by uh, the 40 was that called 0 0.4 40 gram. Okay, so let me keep it here, and then okay, so let's start to record. Oh, hold on, stop it. I just want to see you how the graph goes on. Okay, so just following the instruction here. Let me remove this one. Okay, in case if you want to re-zero the sensor, but you have to let this string loose. Okay, nothing being pulled, so I have left it loose, and then I can re-zero sensor. Okay, and then okay, let's keep it like this way. Okay, and then I will click on record, give it a side push, and just stop when it's 0. Okay, okay, I think you may do it again. Okay, if you are not, we can give it more push. Yeah, okay, so let's repeat it. You can add run. Okay, this is loose. You should not re-zero if there's something is selected. Okay, I have not selected anything, so now I'm just, there is nothing being measured, then nothing selected. Re-zero sensor. Okay, sensor is zeroed. Now let's make it, let's record it. It like now this weight is hanging. Okay, it's pulling our IOLab. I'm not sure if you can see the weight or not, but it's right here. Okay, the weight is right here. The string is being, that's being called. Okay, let's click on record. Okay, and then I will give a push. It was a slight one, but I think it should be fine. Or you can give a harder push and longer as you can see. Okay. Okay, so let's see our region of interest. Okay, this is the one. As we already always know, we are slowing down, and we can select our region of interest by selecting this one. Yeah, so let's select here. So this region was okay. So this was the one. So yeah, so this is our area. We can remove one of them. I think both are fine, but let's remove one of them. Saying this one, I think let's keep the second one. Yeah, or anyone is fine. You can. Okay, okay. Let's keep. Okay, so our area of interest, like we should have stopped here. Our kids should have kind of stopped here and gone to 0, but that's fine. It's negligible. So we give a push. Yeah, as we have said, the velocity will have the same sign that we are moving in. So we are moving toward left. Yeah, that's you can see it's negative sign. Yeah, and then negative. That's when we started the push, and that's the max. Then slowing down means it will as it starts to go to the left. So velocity, the magnitude of the velocity is slowing down, yeah, as it is constantly being pulled by some constant force to the right, which is given by 40-gram mass that is being pulled. Okay, so when velocity is slowing down, we are slowing down, and while slowing down, you can see the force being applied is kind of constant throughout. Yeah, you can see that it should be constant throughout. Like you can just select the region up to here only. Okay, you can select this one also, but this was quite like it should have been gone to 0 like this. So area of region is going from here until it reaches to 0. Okay, if you have, you can take that's also fine, but usually you will get a parallel line if you stop just quite correctly. Okay, and you can see the force, and you can see in the same time the acceleration here. Okay, they are also kind of constant, so I think it's better to consider up to this region for me. Okay, because it will go to 0 when you just stop it, when it goes to the maximum point. Yeah, when it completely slows down, or you gave a push, started to push. Yeah, that was kind of where velocity was maximum. We left it, and then it was being constantly pulled by the force. It was, that's why it was slowing down. It went to 0. Okay, that's the actual point. So while the slowing down reason is this area. So did the sign of the velocity, force, and acceleration agree with your prediction? We predicted, yeah, velocity should have same sign as the direction is moving. I think we have that. Constant force, positive force was being applied to the positive side. We have that, and if we are slowing down in negative, acceleration is supposed to be, we have that one also, or related to the forces. So they both are positive. Yeah, so we'll go ahead. I have the same sign, or yeah, velocity and actually had the same sign or different sign. So based on relationship between acceleration and velocity. So what we have said, if we are speeding up, velocity, sign of the velocity will be same as the sign of the acceleration. If we are slowing down, velocity and acceleration will have opposite sign. Okay, so you may go ahead, write your answers. And okay, I'm not giving full answer. I'm giving the concepts, but you have to write your own answers. Okay, this is an instructional video, not like you have to do the lab by yourself. Okay, and I'm just, because people, students are confused with the selection, because I've seen people selecting the whole region. Okay, that's not the area of interest. So you have to know what is the area of interest. While slowing down, it was maximum here, then it kept on slowing down. Okay, so kind of this will be the area of interest to make the analysis. Okay, so go ahead, write your answers. Don't forget to click on save and go next. Okay. Okay, slide 7. I did 7. Yeah, it's 7. It's more of analysis. Did the force and acceleration have the same sign? Where the force and acceleration in the same direction? So you can see force, accelerations. Compare the sign. Are they in the same direction? Are they both positive or not? Describe the direction, right or left of the force, velocity, and acceleration vectors during the observed. Do they agree? So you have to, yeah, sign. Just to go ahead and make a prediction. Yeah, based on your observation, which of the following statement is or are true? An object with negative acceleration always slows down. Is that true? We are slowing down, but do we have a negative acceleration here now? An object with negative acceleration always speeds up. So can we say that negative acceleration is speeding up? So you might not have seen here, but from the general rule, you can say that, yeah, negative acceleration always, you cannot say that speeding up, slowing down in positive acceleration, sorry, slowing down in positive direction can also result in negative acceleration. So we know the general rule for the acceleration. If you are speeding up in certain direction, acceleration will have the same sign as that direction. If you are slowing down in a certain direction, positive or negative, acceleration will have opposite sign to that direction. Okay, an object with positive acceleration always speeds up. We cannot say that. We have already seen it here. It was slowing down. An object with positive acceleration always slows down. So I don't think any of them is correct. Okay, so explain your observation based on the observations you made. So from the observation you can say that we saw that, yeah, we're moving in, slowing down in negative direction. Okay, we are slowing down in negative, we had a positive, so it doesn't mean we have to, but an object with negative acceleration always speeds up. That's something that is not seen here, I think, but still we can make the predict, like from what we have seen, yeah, previously. Okay, so go ahead, make your explain your answers. Okay. Or I think for this one we can select this reason, yeah. So you can see kind of negative acceleration is there. Okay. Okay. So and sorry, here is also negative acceleration, yeah. So there is negative acceleration, but in this case where we stopped, yeah, we stopped. So when it was slowing down, you see, we are slowing down, yeah, so it doesn't, like, we don't need to speed up in negative direction. Uh, so we don't need to speed up with negative acceleration, always speeds up, we cannot say that, yeah. So we are the more you can see this is in positive direction somehow, yeah, and we are slowing down. So it necessarily doesn't have to be in to produce the negative acceleration. We don't have to speed up. Okay, we can slow down in positive direction and get the negative acceleration. Okay, that is one of the thing. Okay, so this is now velocity is always negative, so we can say but for this part when we stop, slight which was it. Okay, so based on this one, explain your answers from saying the observations here. Okay, and then you can click on save and go next. Again, let me remind, an object with negative acceleration always slows down. Is that true? No, because we slowed down and we had a positive acceleration. An object with negative acceleration always speeds up, so when we stop, uh, but we didn't move to positive direction, so we might not be able to see there, but from our general rule, yeah. But in this graph I was able to show it kind of, when we stop it kind of had positive. Okay, but you might not have this in graph, so but this is not always true. Okay, an object with positive acceleration always speeds up. Positive acceleration always speeds up. So this is a positive acceleration, but it was not speeding up. Yeah, an object with positive acceleration always slows down, so that's also not true. Positive acceleration always positive acceleration, I think in this one that might be true, but from our observation that we have seen, it's not true. Okay, then so follow the general rule. We can have positive and negative acceleration while moving in positive direction. We can have positive and negative acceleration, positive or negative acceleration while moving in negative direction. Okay, speeding up. So none of the above is true. Write your answers and click on the speed and save and go next. Okay, so far we were discussing about like single force that was being applied to the IOLab. Yeah, now we'll discuss about the net force, combined force. Okay, so we might apply some force and the table might be offering some friction. Yeah, so let's discuss about the combined force now. Okay, next slide, slide 9. Once a pull, always a pull. So we are asked to grasp the IOLab in the force sensor, yeah, and then give it a short pull to the right positive direction. Okay, so we'll grab in that I volt into the force sensor, give it a pull and realize it. Okay, so describe the word force versus time graph. So we'll be applying some force. Okay, so it will be positive force. Does it say constant force? I don't think we need short pull. So we'll be applying a force. There will be a positive force in the beginning in the force sensor, yeah, and then after that the force will go down to 0 when you release it, because we are not applying any force into that force sensor thing. Okay, describe the velocity and acceleration versus time graph. So velocity, so when we when we pull with some force, the velocity, since it was in rest in the beginning, it is going to increase first, like increase the velocity will be in positive direction, yeah, and then what happens, it's kind of increasing the velocity, speeding up kind of thing, yeah, and then when we release it, the velocity has to be constant, yeah, since there is no force being like constant. Like if there is friction, it's going to slow down actually, because of the friction. It might slow down because of the friction of our table temp. Okay, the velocity might decrease. And accelerations in the beginning, when we give pull it, goes from 0 to some speed, kind of speeding up thing, so acceleration has to be positive. We are moving in positive direction, yeah, we are always moving in positive direction obviously. And in the next case, base velocity, it will be slowing down. Yeah, so when you leave it, friction will slow the thing down, and then we are slowing down in a positive direction, that will give make acceleration to be negative. Okay, so that's my prediction. So you can predict with the same thing, and then we'll see. So it doesn't, so we assume we have some friction in the tabletop. Okay, I think that's, let's see. Yeah. You can write the prediction and click on give and save and go next, and then we'll see. Okay. Okay, let's do the experiment. Be sure that force sensor has been calibrated. So we did that. As always, there are the force sensor with nothing pulling out just before graphing by clicking the zero sensor. Yeah. So there should be nothing pulling in this one. Okay. And then let's keep it like that way. There's nothing pulling. This is string. We can just let it close. Yeah. And then you don't need the facing line for this one. Yeah. But I have just kept it for there. Then you can click on zero sensor. Okay. Zero sensor. Now let's do the experiment that is has been seen. We have zeroed the sensor already, so we are asked to move in the positive side, pull it and then leave it. Yeah, so we suppose there is a friction of the table top that will slow it down when we leave it. Okay, so click on record, graph the SQI, give the IOLab a very pull to the right and release it. After the IOLab is stop moving, click stop. Okay, it might, let's see, click record. So then I'll give just a slice rule and let it stop. Yeah, that was okay. I think this is what stopped. So let me do it again. Yeah. Okay. So let me. I can remove that also. Or okay. Let's start from here again. Yeah. Just want nothing to come. I can remove it. I can re-zero since nothing is being measured right now. Okay. Now I'll click on record. Give it a short pull and then leave it. Okay. Let it stop. I can just keep it quiet. Okay. Then let's do our analysis. Okay, I hope you already know our region of interest. So this was when we are not moving. I slightly pull it, okay, and then I release it at this point. Then the velocity slightly went down. Okay, although there is no force sensor being measured in the lab, yeah, but the friction is slowing it down. That's why it's going down. Yeah, and it is always moving in positive direction. That's why positive velocity never goes to the negative side. Okay. Okay, let's do the analysis part. Mm. So does the force versus time graph agree with the prediction? Force versus time, we said this will be positive, yeah, and then it will go into went back to zero. When we release it, it was positive for some time, and then it went back to zero for the okay acceleration. So you can, and then for wheel, sorry, for the velocity, we pulled it, we left it here, okay, and then you can do the analysis after you. Okay, for acceleration, you can take it as constant also. It seems zigzag, but and this was kind of slope with a constant slope decrement. Yeah, so you can describe the motion of the eye after it is released. Is it speeding up after we release it? Means this was a point, the speed point. Yeah, it was slowing down up with the constant speed, or moving with the constant speed, or so it was not moving with the constant. It was slowing down. Yeah, so what made it slow down? So that's the analysis you can make. Go ahead, seeing the graph, make an okay. So giving you okay, we can select our region of interest also. Okay, so this is the point. So we were not moving right here, we started to move here. Let me select the whole region, slowing down a little bit more. Okay, that will do. So this was when we nothing, like it was just IOLab was just here sitting, and then I started to pull it. Yeah, I started to pull it, so that's why it got some velocity, yeah, from zero positive side. So that's why I applied the force, some force, yeah. Then I left it. Means there is no sense force in the force sensor. That's zero. Okay, but although there is no force sensor, it slowed down. You see, it was slowing down after I leave it. That's because of frictional force, obviously. And then it was slowing. The rate was kind of constant. Okay, so that's why it has a acceleration in the negative side. Okay, so go ahead, make your write your answers based on the graph and the concepts that I just gave. Okay. Okay, more analysis of the result. Do the velocity and acceleration versus time graph agree with your predictions? So go ahead, answer it. Okay. Measure the average value of the acceleration during the time interval when the IOLab is slowing down. Okay, slowing down. This is the IOLab. So slowing down is this one. Yeah, you pulled it, you released, then it was slowing down. So you can do the average thing of this one. You already know how to do the average using this tool. Yeah, just do when it was slowing down. You don't need to even do full. Okay, you can do from here because it's kind of constant. Yeah. It has to be constant in a perfect world, but okay. That object will slow down if the force applied to the object. So we know if some force is applied, then it will slow down. So once you release, the no force is applied to the force sensor. Yeah, so that's what I already explained. So there was no force being applied to the force sensor that will slow down the IOLab. So what is the force that's slowing down? So as I said, there can be frictional force of the IOLab, that is like stopping its, like, not, yeah, slowing down its motion, yeah, opposing the its regular direction of the motion. Go ahead, so write your answers based on those, and click, do not forget to click on save and go next. Okay. Okay, moving on to the next slide. Okay, so they are talking about net force and Newton's first law. So you can recall Newton's first law. Okay, so which is generally the object will continue in its motion if unless any external force is applied to it. Okay, like with its motion, it will not stop, it will continue in its motion at the same velocity unless any external force is applied to it. Okay, it is possible to have the IOLab to move at a constant velocity, zero acceleration, after it is pushed and released as shown in the figure above. So they want us to give a slight push to the IOLab and make it move in a constant velocity. Okay. So so the main idea is here is we are trying to make net force equal to zero. Okay, describe the direction and magnitude of the force you would need to apply so that the IOLab will continue to move with a constant velocity after it is given a brief push. So like we did before, so we pulled it, like, and like giving a force from here. Okay, we are moving in positive direction. For instance, if we give a push from here, if we do not have this thing, it's the IOLab, it's going to slow down. We already saw that. Okay, because of the friction. So we need to give a force. Okay, so we have to make a net force being applied during the motion to be zero. So what we can do is, like, we can pull it by the, we can give frictional force is going to opposite, yeah, towards that side. So we can give a force that will be applied towards this side but in equal in magnitude to the frictional force, so that by net force being applied goes to zero, and then it will have no acceleration, yeah, constant velocity will be there. So that's the whole idea. So we need these things. Okay, and then we'll, the general idea, as I've said, we'll try to have some constant force that will cancel the frictional force and let it move in a, with zero acceleration with a constant velocity. Okay, and the direction of the force that we apply have to be in the opposite direction to the frictional force, obviously. Okay, this is what we will be doing for the activity. So you can create a small envelope to actually I just, let me see what I will use to, or you can use something that you got in with your IOLab. Yeah, while you got the device, you can put the coins in here, use the paper clip, yeah, and then just hold it with the paper clip, and then attach it to the one inside of the string. Okay, for this one I mean. Okay, then you can put, we have to put coins in here, giving a force that will equal to the frictional force that is being applied to the left. Okay, we'll pull it to give the constant force toward the right. Frictional is being applied to the left, and if they cancel out, if we are able to have uh, in such a case that net force applied on IOLab is zero, we can have a constant of velocity when we just give a slight push. Okay, that's the whole idea. Okay, let's go to the experiment. So how you have to set up is, like, you have to put the mass of the coins. We have kept it here. Okay, mass of the coins just barely equal to that, so that the IOLab will not move. Yeah, so if the mass is greater than the friction that is being offered by that, that will yeah, what's that called, pull your IOLab and it will keep moving. So you have to keep the mass of the coins such that if you keep it here, it barely moves. Like, it will not move. Okay, it will just, if you give the side push, it's going to move, but the mass of the hung, it will barely move as it has been saved here. Okay, so make a mass. So your IOLabs should not move in the hung mass of, with the hung mass of the coins. Okay, if you just keep it straight raised and just slightly keep it like this way, you see, barely moves. And then it should not be too less also. Okay, less, or if you have less also, that's not also going to be. Whole idea is we are going to pull with certain force that is equal to the frictional force, yeah, like offered by this ram, but in opposite direction to the holes over there. Okay, so next one. So if we want to reach zero sensor, I have already said it has to be in such a way no force is being measured. Okay, so let's re-zero it. So I was just making that loose. Okay, then you can click on re-zero sensor here. Okay, now let's run it. Yeah, it should barely move. It will move if I just give a slight force also. So I'm just, you see, that's moving. So let's make it like this. Okay, and then we want us to record it. Okay, why is not being, okay, it's not being shown. Yeah, so let me record it. So let me turn it on. So I might have to re-zero because it was not there. Yeah? So there is no force being pulled in the force sensor. Re-zero it. Okay, and then you put it. Okay, just keep it here. That it slightly moves. Yeah, like this, and then okay. Okay, now do the experiment. Yeah, you can click on record and give the IOLab a brief push toward the right. Okay, let's click on record. Okay, and then we'll click on record, give it a brief push. Let's just leave it, like let it move for some seconds, and then okay. So let's move on to the analysis part now. So I hope you know where is the area of region of interest. Yeah, is the velocity constant when the IOLab is released. So this was just where it was just keeping still. Yeah, and then we gave the side close. So that's how it had some velocity, and then this is until it stopped. Okay, so area of region is from this part to up to this part. Okay, so you can see the velocity, is it constant? So you can see it's kind of constant. Yeah, in theory it might be difficult to have perfectly constant. So this was the reason of interest. Okay, it stopped when we stopped it when it here. You can see the acceleration was 0. Okay, and the force, obviously it has, the force has to be something that you applied, force sensor, the constant thing we are applying. Yeah, and say frictional force cannot be measured by this one. Yeah, but this will measure only the force that we applied with the coin thing. Okay. So you may go ahead. Is the velocity constant, or so is the velocity not constant? Experiment by changing the hanging coins onto. So we need to have a constant velocity. We already said our goal has to have constant velocity. Yeah. Okay, let's select kind of area of the interest. Okay, area. So okay, so let's select it from here to here only. We don't need more than that. Okay, so the area of interest was like this one, constant velocity. Yeah, kind of perfect. You might not have it perfect, but try to have as constant as possible. Okay, average acceleration. So acceleration is here. You may do it the average. Okay, so you may do it from, sorry, oh, I should not have done that. Okay, let me get it back. To get the graphs back, I just clicked on this x-axis. Okay, now let me select the area of region of interest again. Okay, if you can make analysis without selection, that's also fine. I just wanted to make it clear. Now for doing the average, we can use this tool. Yeah, we need to do the average force and average acceleration. So that's our average acceleration. So you can just kind of select, you may select from here to here all, but that's okay since it's constant. So how much is the average? You can see average acceleration is how much? This is here, yeah, 0.078 meters. So kind of constant. We can take it as sorry, you can take it as 0 kind of. Okay, so in theory it is supposed to be exactly 0. Okay, so force, there will be some force applied. Okay, 0.058 newton. So that's being applied. That was given by our, so that means our ramp is kind of smooth. Okay, it's more smooth. Okay, so you may go ahead, write your answer. For that's answer for me. You may have a different thing. If you have more friction, the force here will be greater. Okay, higher. For me, I had I think kind of more smooth surface. That's why it was just not. It could have been greater. Okay, but for now it's okay. Average. You can write your answers. Okay, and then click on save and go next. Okay. Okay, more analysis. In this activity, IOLab come to rest sometime after it was released because of the frictional force acting to the left. Yeah, in this activity, the IOLab continues to move at a constant. No, in previous activity that came to rest, but in this case, it continued with a constant velocity y. We applied the same force as frictional force to the right. So like that will cancel out the effect of frictional force. Yeah, so that net force on the IOLab will be 0. So which is actually the force applied by force given by our coin. Yeah, so applies force during the motion. Okay, so what two forces are acting on the IOLab as it moves at nearly constant velocity? So one is frictional force, other force is the friction force that was given by the coin. Yeah, what can you say about the magnitude of the frictional force to the left and the force applied by the fixing line to the right? So as I've already said, if we want to have a constant velocity, uh, no acceleration, zero acceleration means combined force has to be zero. Yeah, if there is some force, there is going to be some acceleration there. Yeah, but I mean the combined force. Okay, no, we cannot just say some force, because you might see some force here, but the net force that is applied to the IOLab has to be zero to have zero acceleration. So magnitude have to be equal, but in opposite, like to be equal. Yeah, but they have to be in opposite direction so that they can cancel out each other. Go ahead, write your answers and move to the next slide. Clicking on 7, go next. Okay. Okay, more analysis based on the graph. In the previous slides, we found that force applied to an object is proportional to the acceleration of the object. We did that, yeah, Newton's second law. In this activity, you found that acceleration of the object was nearly zero. What net force produces zero acceleration? So we already said it has to be zero, yeah. So you may go ahead, write your answer. Okay, we set Newton's first law in terms of the net force on an object that moves with a constant velocity. So okay, kind of, I already said it. An object moves with its constant velocity unless an external force is applied to. Okay, if like, or if the net force in terms of net force means, so if the net force is zero, that is applied on any object moving with the velocity, then it is moves with a constant force. Okay, constant velocity. If a net force applied to an object is zero, it will move with its constant velocity that it is moving on. Okay, based on your measurement, what is the magnitude of the frictional force x and how you find the value? So we already said that, yeah. So net force has to be zero, so you had some force applied and the frictional force has to be in opposite direction, but the magnitude has to be same. Go ahead, write the answers, click on 7, go next. Make sure you get the concept. Okay, net force has to be zero to get the constant velocity, means zero acceleration, and since the friction is opposing the motion of the IOLab, but we need a same force that can cancel out the frictional force, which we did by putting the coins, yeah, the force that was applied by the weight of the coins. Okay, you can go ahead, write your answers and click on 7, go next. Okay, now we have been seeing the relationship between the acceleration and the force. Yeah, now we'll see what will happen with if we change the mass. Okay, we'll keep the constant the force being applied same, but we'll change the mass and see how it affects the acceleration. Okay, when you change the mass, because we cannot, if we apply the same force uh, to a simple IOLab, okay, and same force to a big bus, big truck, big car, so acceleration is going to be different. Yeah, since changing the mass. So let's see the relationship between that. So we'll need different masses in this one. Okay, so bus, we can use water bottle. This says 500 milliliter in size. Okay, two plastic water bottle. Okay, so we have to get these things. Okay. Okay, prediction time. Yes, the real-time physics. What usually does is like we'll predict first, then we'll see the experiment, and then as light. Yeah, so we'll do our prediction. You can change them. You apply a force to the IOLab and measure its acceleration. Now you double the mass of the IOLab, apply the same force. So force is constant, mass is changed. What will be the acceleration? Okay. Then in general, also you can make the prediction. Is it going to decrease? Is it going to stay same? So go ahead, make the prediction, and then we'll see our prediction in the next when we do the experiment. Okay, when you make the run of the IOLab with different masses. Okay, we can follow the regular, what's it called, regular zeroing thing. Yeah. Sorry, calibration. You can calibrate the IOLab. So follow the instruction. Nothing should be measured, and with the IOLab on the tabletop with the screw I pointed upward, and there should be no force. Right now I have the coins from before, but there should be no force. So let me let it loose, and then we can click on re-zero the same. Oh, let me turn it on if it's already off. No, sorry, that was the border. No, it's not in this one, so it might be in the next one. So click on save and go next. Okay, we are a bit here. We can re-zero the sensor. Then we have to get the weights that will change the force. Okay. Sorry, that will change the mass. Sorry, of the IOLab, mass of the IOLab. Yeah. Okay, now let's create the masses like one which we'll need during the experiment. Okay, so for the first one we have been asked to click record lift the, so after this is visualizing the sensor, I think. So we'll keep it like this way, yeah, without nothing being measured here. So we can zero the I think it's better to have it like this way here. Okay, we zero the sensor, nothing is being kept, like it's not being pulled or anything is, yeah, but I hope that after the calibrated thing and record for a few seconds. Okay, let's click it, then you can left it and just record this about getting the mass of the IOLab. I did it for a whole second, you can do it for some second. Okay, then you can go ahead, find the average as always, yeah, just do the average thing. Okay, and then get the value here. Okay, okay, and then write the average here. Now we have to make create the masses. We need twice the mass, thrice the mass. Yeah, so we'll create the mass with the mass equal to the IOLab. So you can use the box with some coins or stuffs in it. Okay, or the water bottle like this. So I have created with the water bottles 200, one having around 200 milliliter and the other around 400. So yeah, let's follow the instruction. Okay, after you have written the average weight of the IOLab, yeah, let's follow the instruction of the paper clip to the side of the cardboard. So like we are creating the mass similar, so it's same to the IOLab first. Okay, so hold the IOLab with the screw eye pointing down. So what we can do is we can do it like this way. Okay, pointing down, IOLab screw is pointing down. Then they, okay, pointing down is like this way. Okay, then they ask us to, okay, this is an important step here. Okay, so they have said us to re-zero the sensor. Okay, if you click here with being something selected here, it will lift that. Okay, so let me do the error, and then you see it going down. So that's not the way, something being selected here, we cannot re-zero. Re-zero means when something is measured zero, we can do that. Okay, I can just click on re-zero sensor like this. So I select the region where the zero is being measured. Okay, or what you can do is, no, so actually this is not here. So what actually we can click on when it's on here. This has to be turned on zero sensor. So so or what you can do is, like if you had this selection, yeah, so while you can just click somewhere outside, yeah, double click, and then the selection will go, then you may click on zero sensor. Okay, it lifted somehow, but yeah, that's okay. Or you can select some where there is zero, yeah, and then you can click on zero sensor. Okay, after that, so I have created the water bottle. Okay, the mass that is equal to the IOLab. So I have rezeroed the sensor. Did it turn off? No, it's on. Yeah, so okay, that was the first one. So let's add run. Okay, let's reset the sensor again. Okay, I have rezeroed the sensor, and then let's, okay, I can record it first, and then I can, or I can do it the other way also. Okay, and okay, so this way will be the, okay. Okay, then click record, hook it into, okay, I think it's more difficult. So or next thing, or we can just, okay, let's, we can measure it in the beginning also. Yeah, there is no harm in that. Okay, so let's remove the second one. Okay, and then let's add run. Oh, we don't need to add run now. I can reserve the sensor. Okay, and then let's keep it in here first. Okay, that should also work. Or you can start recording and then do also. Then click on record. So you can see it's kind of similar to the weight of the IOLab. Yeah, you can stop that one. Okay, they expect it to be similar, but we might not have exactly the same. But okay, it's around 200 milliliter lower. Okay, okay. No, that's not. We can just complete it. That's not needed also. So we had kind of similar. Yeah? It's not same, but it's kind of similar. So what was first one was, yeah, you can do the average again. Yeah, for the average, you can select this region, average the force. Okay, I think that was for 200 milliliter. Okay, and then you can write your average. Selecting this one. Okay, okay. Oh, it's not selected. Or is it not selected? Okay, so you can see the average here, yeah, for the both of them. And that is the only way. Okay, and then you can double click anywhere. Okay, and then the next one, so we'll be doing same thing for this one. Average weight for the one with, we'll use, I have used 400 milliliter with the water bottle. Okay, and then I okay, and then I'm going to with the 400 milliliter water bottle. Let's measure. You can do it. I think you can go ahead do this same process. Okay, and then we can go to the experiment with different masses, but we'll apply same force. And for we are asked to constant force of by measured with what's it called 0.6 grams. Yeah, for that I have used the IOLab itself. Sorry, IOLab box. Okay, in the IOLab box I just put a couple of coins and create around 60 gram mass so that I can use it when I need to pull it. Okay. Okay, as I have done for two of them, let me do for the third one how I created the mass that is equal to 2 times the IOLab. Okay, so following this step again, nothing being measured. Yeah, pointing the screw down, zero the sensor. Okay, but make sure nothing is selected here. Okay, okay, zeroing the sensor. Then let me hang it first. Okay, you can do click record and hang the mass also, but since I had a problem for doing this for the whole second, I can do it in the beginning. Also, yeah, I hang with the IOLab. Can you see it? Okay, I'm just hanging the water bottle with 400 milliliters around water. Okay, wanted to show you. Okay, I think that's a good review. So then click on record. Oh, it's still, you should have a straight line because I'm flipping. That's why I didn't have it. Okay, you can have a straight line also. Okay, and just does it happen or it changes? Okay, it's going to be a straight line if you hold it straight, but that's okay. Okay, I can keep it now. Hold on. Alright. Okay. Okay, if you do, you might have a straight line also. Yeah, you will have it like it was what's it called hanging while it was moving. Yeah, so that's why it was not constant. So you can go ahead. It's kind of double from this one. Yeah, so you can go ahead to the average. Yeah, and okay, I think I can have for three. The first one, second, and third one. Like let's see the last one. The last one is kind of double. Yeah. So I've created the mass. You may write your values and just click on save and go next. Okay, do not forget that one. That's important. Okay, let's do the experiment by applying same force two different masses of IOLab. Okay, like we'll change the mass. IOLab will have the same mass, but we'll add masses to it. So let's start. So for 60 gram, as I've already said, I use the same cardboard that IOLab came in with some coins in it. Okay, I need a couple that book clip. Okay, I just put it down so that I can. Okay. Okay, so just write it down. Just put it down. Okay. I'm showing step by step. Your graphs in during the experiment will look different than mine. Okay, like the nature will be same, but the values will be different. So we cannot have same values exactly same. Okay. Okay. So let's follow this step. So I think we have to zero the sensor first, but while zeroing the sensor, as we already know, it should be loose. Yeah, there should be nothing being measured. So let's make it loose so that there will be nothing being pulled that one. Then we can re-zero the sensor. Okay, and then let's follow the instructions. So we want us to record release allow it to move across the server. Okay, so I have already zeroed. Now we can just keep it like this way. Okay, so let it move it from some space so that we will have some graph. Okay, okay, and then I'll click on record and release it after some second and then stop. Okay, before it hits. Oh, I should have shown you the graph. Sorry about that. Okay, so it's okay. I think I got it, but okay, I can do it again. Make it sit there. Okay, and then okay, let me redo it so that you can see. So I've taken add run already. Yeah, so we have to re-zero the sensor, the same step. Like while re-zeroing, it should be loose. Yeah, nothing being pulled, nothing being selected in the graph. Okay, and then let's take it our usual place. Okay, and then I can click on record. After some time, I will let it go, and then I'll stop. Okay, if there's a bump, we can ignore that also. Okay, so kind of grab that we'll get. Okay, so which one to keep? Both will be fine, but okay, let me keep the first one. I just wanted to show during the run. That's nothing. Okay. So let's do the analysis. So this was velocity. So it was constant force was being applied. So it is linearly. Yeah, it should have been kind of constant, but we can take it as kind of constant. Okay, take it as constant kind of. And then this is the force that is being applied during the motion. So area of region of interest is this one only. Okay. So they want us to do the average. So you know how to do the average already. Click here. Do the area of region of interest is during the IOLab moving. So this is where. So just this part. Okay, don't go beyond here. Beyond here, you can just select in between here to here. Nothing more. Okay, after you start, you don't need to do it from here. Okay, just do it up to this part only. Not even the constant thing, because it has to be linear. Yeah? So from here, actually it would be up to here, but it was supposed to be increased like that. But that was when I think when it bumped in the ground. So from here to here would be okay. Okay, go to the average, and you can go ahead, click on save, and go next. Okay, as we already know, we are applying the constant force, yeah, but to different mass, yeah, of the IOLab. So what you can do, so you can see already I have taped the water bottle, so you can take the air out. I have not done that, yeah, to the top of the IOLab, and we'll be doing the same thing as we did when that was a same was a single IOLab only without mass being added on. Okay, so this water bottle has same mass as the IOLab had. So let's do it. So first. Okay, so without okay, there should be no force being applied. Let's keep it like okay, no force being applied. So that means making it loose the IOLab sensor part here. So let it make loose. There's like it's the string is loose. It's not it has nothing. So that I can okay, it went off. So let me turn it first. Okay, turn it on. Okay, it's paired now. Okay, then I can just make it loose and then re-zero the sensor. Okay, sensor is zeroed. I can add run and then re-zero the sensor. Okay, and then following the same step, I'll just keep it like same force. Yeah, we are up. Sorry, we are pulling it with the same force. So let me keep it same way. It was kind of like this here. So the mask is better. The mask not to be hanging. So somehow, okay. Okay, you do while you're doing, let the mask not be still. Okay, that would be good. Oh, I already did that. Okay, and then let's record it. So okay, oh sorry, I could have left it earlier. Okay, let me do it again. I think that would be a good thing. So remove the last one. So lose the string so that you can 0 okay, you can 0 sensor. I have made the string loose. Okay, and then keep it in the same position like before for the first one. You can do it quickly. Okay, I'm taking time so that you can have the good result. Okay, and then it's better to have the mask not hanging. Then record it, leave it. That's it. Okay, so you can see you can already see the difference. I have just taped it. Okay, and make sure that your wheels are not taped. Okay, because they have to move. Okay, so you cannot. It will be a kind of a straight line. Okay, if when we do it, it should be like in theory, it not perfectly, but kind of a straight would be there, and the acceleration is supposed to be a constant thing here, although I might not have got here. It should be kind of a linear thing. Force is kind of constant thing. It was like hanging, what's it called, moving. Yeah, so but it is still it is better result. So and this will be a constant around constant line. Okay, so take it up to here only. It should have increased, but I think this was after the bump. You can start from here until here also. Okay, so while taking the average, so you can already see we applied the same force. Yeah, force was not different. If you see here, this is kind of similar force. Yeah, so that was the force being applied. It's similar force being applied. The acceleration, so you can see it was like you can compare it with this region. Actually, that's the better part. Yeah, because this was moving until this region only. that was the linear thing. If when it get straight, you can avoid that region. Okay, and so because acceleration is supposed to be a constant thing. Okay, it is kind of constant from here to here. Okay, so you can compare here. Acceleration was this, and then you can take the average for the first one. For the second one, when you had masses, double IOLab masses. Now let's see. Okay, mass says added to the IOLab. In IOLab we didn't add anything, so we consider it as one IOLab mass. You can take the average, which is the first one, average of the IOLab force, yeah, average force. Second one, and sorry, average acceleration, you will get it from here. So make sure your region of interest. Okay, so take this as a region of interest, because acceleration has to be kind of constant, and it has the velocity will have a slope, linear constant slope. Okay, so it is up to here, it could have been up, you might end up having it up to here also. Okay, so it should be like that linear thing, and the same thing goes here. So take it when it's constant and straight, so something like this, and then you can write your values here, write your values. Be sure, like making the selection, if you go beyond this one you will get 0. That will affect your average acceleration, yeah, for the first one. I mean, if you go here, if you go beyond that, that's 0. So okay, the region of area of interest would be with the positive constant slope. Okay, and then do the same thing for the third one. So now you need to have, instead of this one, you need to have a water bottle that will have two, yeah, almost, we had one, then yeah, you will replace the this one with the one with third, what's it called, yeah, next one that we had twice. Yeah, so that will make it 3 times IOLab mass, and then you'll have result for this one. Then you can click on save and go next. Okay, the whole idea is, what we are trying to see is when we apply a constant force, okay, to an object, but change the mass. With changing mass, what kind of acceleration is produced? Does it do the same? It will decrease. Okay, okay, just to show you the third one. Okay, so for the general idea of the, okay, let's show you. Okay, so when I did for the third one with water bottle, twice the mass of the IOLab, so that the total will be 3 times the IOLab. Yeah, we have the IOLab itself and twice the mass of the IOLab added on the top. So you can, I've already reserved the sensor with the first thing here. I can click on record, and then I'll just let it go. So you already see some change here. After that we can do the analysis. Okay, so while, okay, I think force has to be kind of constant, so it might have changed. So but it has to be kind of constant. It went to 0.53, which is not expected. So okay, so let me, okay, I think I got the right one, but let me show you. Let me remove the last one with the two IOLabs. Yeah, so sorry, I mean 2 mass of the IOLabs on the top of IOLab itself. So let me remove that one, and by putting it like this way, let's, nothing like a string is loose. Okay, nothing is being pulled, so that I can re-zero. Okay, and then I can put, okay, leave it like the same surface, take it to the side so that it can move. Okay, let me record it, I'll leave it. Okay, now you can see kind of idea, you already have kind of idea. Yeah, so during the motion, yeah, see, during the motion, that was our motion. So you can see the force, how much of the force is kind of constant in all 3 cases. Okay, so as you can see the rate of change of velocity and the acceleration, the last one. Yeah, so take it, you might get it a constant thing also in here, but if you don't get, also we'll take the average obviously. Yeah, but in theory it has to be a constant thing since the rate of change. So you can see the change in the velocity with the increasing masses, so go ahead, write your answers in there. Okay, I just in there, and then your answers might be different. I have written something, but your answers will be different obviously, because your masses will be slightly changed here. Your velocity force has to be nearly constant. So you can go ahead, write your answers, and then pause them, and then sorry, yeah, and then click save and go next. Okay, after that, from the values we had, you can answer this one as, does the acceleration of the IOLab increase, decrease, or remain the same as the mass of the IOLab increase? So during the motion it is constant, but when you increase the IOLab mass, so it, you can make a decision based on the values that you had in slide 22 also you can from the graph also. Yeah, so you can go ahead, click, write your answer, and then click save and go next. Okay, so it is asking, when we increase the mass, we applied the constant force here, we increase the mass of the IOLab, so what happened to the acceleration? Did it decrease? increase or remain the same. You can go ahead. It's not asking for a single run, comparing 3 runs that we had. Okay, what happened when we increased the mass of the IOLabs? For a single, every run it was a constant. Okay, for a single run it was constant for the first one, constant for the second one, constant for the third one. But comparing them, when we increased the mass of the IOLab, what was the effect on the acceleration when we applied with the same force? Okay, after that you have to use the graphical analysis tool, anything, okay, and then use the fit routine of the, so you will fit the data, average acceleration for the IOLab mass, okay, with the constant force applied. So you can write the average acceleration you got and the IOLab mass so that we can have the relationship, okay, use the fit routine versus the mass of the IOLab, different linear to power. So I think you can go ahead, okay, when you have found the best fit, save the graph, then you can click on save and go next. So you have to answer which graph was fitted. Did you fit like this or like that, or is it kind of yeah, this one, or and b is constant. So y is linear function which decreases. So go ahead, you can fit like make the analysis which one fitted. Okay, after you do the linear fit, I think it has to be a linear fit, but the intercept might not be there. Okay, because y force equals k times x. So mass times acceleration. That's second law. Yeah, f equals ma. So if force is constant, it has to be inverse thing. Okay. Mm. After that, what appears to the mathematical relationship between acceleration and the mass of the IOLab. So you can go ahead, write it here. Okay, and then so, one of these. Okay, so I think it has to be inverse. Y equals is a function of decrease of frequency. Mathematician might be y equals b plus c x, where is an integer b equals 1, b equals 0, and the relationship becomes y equals c times x. So I think that could be a thing. Okay, inversely proportional. So yeah, I think that would be more, that makes more sense with the second law of Newton. So you can go ahead and do your calculation. Okay, and then let's see for the next one. I have already clicked saved and go next. Okay, so you give your analysis in the lab of the exercise. What's proportional to the force applied to the IOLab? Yeah. So it's in odds, the gender. So I already said summation of equals sometimes a. Yeah. One is inversely force. It is acceleration is directly proportional to the force. Acceleration is inversely proportional to the mass. So based on that, summation F is equal to ma. So you can go ahead, write your answer, and then click on save and go next. Okay. And then that should be the final slide. You can export it to PDF and save it. Okay. Thank you.